Hello everyone. Today I'm going to talk about scalable image transmission using semantic communication enabled autoencoders. So my name is Professor Anil, a professor in video coding and communications here at University of Strathclyde in Glasgow in UK. Before we talk about the topics, let me give you an introduction about my research group here in Strathclyde. So this research team is all about multimedia processing and communication. So I have about 20 members working on different aspects of media processing and communications. So main research areas we are working at the moment is on semantic communications, video coding and communications, machine learning for different applications, and future digital advertising. So the main bulk of the people are working on semantic communications, where we talk about semantic image and video transmission and how we are going to make use of semantic communication concepts in image and video coding and their transmission over different network types. And semantic noise modeling, this is one of the most promising areas where we lag at the moment. There is no proper noise modeling system for semantic communication. So this is one of the other key areas we are working on. And the other main aspect is the quality modeling for semantic communication-based media applications. So right now, since noise modeling has not been done properly, so there is no quality metric available for measuring the semantic noise in end-to-end communication system using semantic communications. So this is another area that we are working on in the semantic communications group. And the next one is the machine-to-machine communication using semantic communication applications. So how machines can communicate between each other using semantic communications. And finally, semantic communications will be used for upcoming 6G applications, and how we can make use of these 6G applications using semantic communication will also be under the discussion on the current semantic communications research. So those are the main highlights of what we are doing at the moment within the group. If there's anybody who wanted to collaborate with any of these topics, so you are welcome. And my contact details are given in this presentation. So let's briefly look at how the evaluation of communication happened over the last 40 years. So we started like about 43 years ago. We started with first generation mobile networks where our intention was to transmit voice between two endpoints. And we defined them as the first generation of mobile networks. And then after 10 years or so, then we had the second generation mobile network, where we increased the bit rate up to 250, up to 50 kilobits per second. Mainly, we were targeting about circuit and packet switching network. And main target areas was text and voice transmission again. And after another 10 years, we had the third generation mobile network where we increased the data rate to 20 megabits per second using AMPS, UMTS, CDMA, and WCDMA technologies. And our main target again, the voice was the main target. And on top of that, we also tried to use multimedia transmission between two endpoints. The main technology that we use is packet switching and broadband. So another 10 years later, in 2010, we had the fourth generation mobile, which used the full IP and ultra broadband technologies. We managed to increase it up to like 1 gigabits per second. There's a massive increase of the data rate from 20 megabits per second to 1 gigabits per second data rate. And the technologies that people have used is MIMO or TM turbo codes and so on. Main target application was again the voice. On top of that, the multimedia, HD videos, mobile TV, and mobile internet was but they were the main target applications on the fourth generation of network. Another 10 years later, down the line, then we witnessed the fifth generation mobile networks, where we managed to increase the data rate from 1 gigabits per second to 20 gigabits per second. And the main technologies that we targeted was the millimeter wave, massive MIMO, and nomad technologies, and targeted applications were VR, AR, 360 video, and other types of video, wearable devices, vehicle communication and vehicle control center communication. So we call it V2X communication, smart cities, telemedicine, IoT, and different other applications which we are started to witness nowadays. And increasing integration with AI and machine learning, cloud and network slicing, they were the main key technologies compared to the fourth generation network we had about 12, 13 years ago. And the next generation of mobile, which we hope to get it evolved in another like 7 years from now, in 2030. And people are talking about to increase the data rate somewhere close to 1 terabits per second. It's a massive again increased from 20 gigabits per second to somewhere close to 1 terabits per second. So the targeted applications were space tourism, tactile internet, fully automated cars, holographic verticals, deep sea insight, digital sensing, digital twins, etc. And a lot of media applications on top of these as well for different uh, applications of different domains. So targeted technologies is like quantum communication, SMBMO, and this AI machine learning and blockchain technologies. So compared to fifth generation, fuller integration with AI machine learning intelligence is expected to happen in the sixth generation. And on top of that, so semantic communication will be another main pillar of 6G technologies. So that is being proposed at the moment. So let's start with the basic communication system. Anybody know who are familiar with the communication system? So this is a very simple end-to-end communication network using the source and the destination. So we have the source on the left-hand side, and then we encode the source information, and then source information is channel coded to protect the data or which is carrying over the noisy channel. And then we have a modulator. Everything is happening at the transmitter side. So then whatever the signal is modulated will be passed through the noisy channel. We call it physical channel. And at the receiving side, we do the inverse operation. So we demodulate the signal, then channel decode it, and then source decode it, and then send it to the destination for reproducing the signal. So this is a classical end-to-end communication system in a very simplified format. So if you communicate these basic concepts, and about 70 odd years ago, Shannon has defined 3 layers of communication system. We define them as technical level, how accurately can symbols of communication be transmitted. So this is what we have been witnessing over the last 60, 70 years. So when you transmit a signal from A to B, so we create symbols using modulation, and then symbols are carried over the noisy channel, and at the receiving side, we try to reproduce these symbols and regenerate the signal, which is quite close to the original signal which we generated at the transmitter side. So this is called the technical level of transmission. And then on top of that, he proposed another level, which is called the semantic level. So the idea of the semantic level is to how precisely do the transmitter symbols convey the desired meaning. So that was the idea of the second layer. And the third layer on top of the semantic level is defined as effectiveness level. How effectively does the received meaning affect conduct in the desired way? So these are the three stack of framework they proposed about 72 years ago in 1949, 48, that during that period. Uh, and he proposed these three concepts. And so far, like I mentioned before, we have been only using the technical level for end-to-end communication. But however, with the development of the machine learning and AI technologies, people have started to look into the second level, which is the semantic level. And because of that reason, semantic communication has been gained a lot of momentum over the last 2 years, and because that will have a lot of applications, especially in the media domain, IoT domain, and the 6G applications. So one of the main problem currently we are facing is the system resources, mainly the bandwidth, because multimedia tend to generate very high bandwidth requirement, and current technical level may not be feasible for high volume bandwidth applications like high resolution video transmission. So this is what the Shannon theorem, capacity theorem says. The Shannon capacity theorem defines the maximum amount of information or data capacity which can be sent over any channel or medium, wireless or coaxial or twisted pair or fiber, etc. The capacity is defined by C is equal to B times the log of 2, 1 plus S over N, where C is defined as the channel capacity and B is the bandwidth available for data transmission, and S over N is the signal noise ratio. S is defined as signal power, and N is the total noise across the bandwidth. So now you can see that to maximize the capacity of the channel, either we have to increase the bandwidth or signal noise ratio. So if we increase the bandwidth, which consumes system resources, there's a limitation factor. And on the other hand, if you want to increase the S over N, then the channel capacity can also be increased. So that means we are increasing the transmitted power, which is again to be a constraint. So that's why the capacity has been limited by the bandwidth and the signal power. So channel capacity can be increased by increasing the bandwidth, increasing the signal power, or decreasing the noise power. So basically, these are the constraints. That's why people have been looking at different avenues to increase the capacity, hence the semantic communication concept. So like I mentioned before, this is the systematic diagram in very briefly to introduce the semantic communication. So the lowest layer is a technical layer. Like in the previous diagram I told you before, we have the channel encoder, modulator, and the physical channel, demodulator, and channel decoder. On top of that, then we have a semantic encoder, so which encode the source information semantically. And then we have the semantic noise, and then the semantic channel. Shared knowledge is happening between the encode, transmit, and the receiver. And at the receiving side, so we get the semantic decoder. So what we extract the semantic information from the source, and then together with the technical layer, we pass that information to the decoder. And one of the key difference here is we have to share some of the shared knowledge between the transmitter and the receiver. For example, if we are capturing some images in the beach, so then we have to inform to the receiver that I am capturing some information in the beach side. So then decoder knows that it is happening somewhere close to, somewhere within the context of a beach. So this kind of side information is shared between the source and the destination. So now our key challenge is happening in the semantic layer. So here within this part of the presentation, I'm going to talk about how scalable image transmission can be happen using semantic communication concept. So semantic communication based scalable image transmission using autoencoders. Here we have used semantic communication enable autoencoders to transmit the scalable images between 2 points. So scalable image coding is quite important, especially for different applications where in this part of the presentation, we consider only SNR scalable or quality scalable image transmission, and how that is impacted by the noise and the system performances. So state-of-the-art codec at the moment is available from JPEG or JPEG 2000, and within this context, we are comparing results against the state-of-the-art. So this is a classical autoencoder-based image encoding framework. We have different 2 convolutional layers together with 2 max pooling layers to generate a latent vector with size of 64 by 1. And then we at the receiving side, we have another two deconvolution layers to convert it back to the received image, which has a very high correlation with the original image. So this is a snapshot of the autoencoder that we have been using in this framework. And what we are doing here is, so we use an autoencoder to generate the base layer. So this is the base layer. So we have this autoencoder and the autoencoder decoder to generate the base layer. Once we generate the base layer, we take the difference between the original signal and the base layer to generate the next level signal, which we used here. And then we have a residual encoder one, which encodes the residual using a higher quantizer to generate the first layer of the enhancement signal. And then this enhancement signal is again subtracted from the remaining signal, and then generate the second layer of the enhancement layers, and then so on. It will be continued until we reach the last layer enhancement layers. So here in this proposed framework, we have used one base layer and then 4 enhancement layers to demonstrate the effectiveness of the proposed algorithm. So this is the corresponding decoder. We have the auto decoder at the receiver. So we take the latent vector and then generate the base layer here, and then subsequently we generate the we decode the residual signals and then add them accordingly to generate the next level of decoded information. One key thing here is like we have used JPEG encoders and decoders to encode and decode these residual signals, whereas for the base layer generation, we use the autoencoder train for encoding and decoding the base layers. And this is the results that we generated. On the left-hand side, the PSNR is indicated. On the right-hand side, SSIM is indicated. So here we have used PSNR and SSIM as the main two objective quality metrics to evaluate the performance. So here we have 4 graphs. The solid ones represent the PSNR graphs, and this purple one and the orange one generates the proposed one and the JPEG equivalent JPEG system. So you can see that PSNR of the proposed system is much higher than, especially at the lower bit rate compared to the higher bit rates. When we increase the base layer to the enhancement layer 4, we consume more number of bits, and also the quality will also be increased. So this is under no noise conditions, and similar observation is happening at the with the SSIM as well. You can see that the purple dotted one represents the SSIM for the proposed one, and whereas the orange dotted one represents the equivalent JPEG system with the SSIM. You can see the performance of the proposed one is very high compared to the state-of-the-art JPEG scalable project. And this is representing the bits per pixel or VPP for the base layer, enhancement layer 1, 2, 3, and 4. You can see this again without noise. You can see that the proposed system consumes very little bits per pixel compared to the equivalent JPEG system. And on top of that, we have also used unequal error protection and equal error protection to protect this data at different levels. So being the most important layer, the base layer is protected more compared to the enhancement layers. Subsequently, the protection for the enhancement layer 1 is higher than 2 and 3 and 4, and 2 is higher than 3 and 4, because when we go down from top to bottom, so we lowered the protection level because there's no point of decoding R4 if we can't decode R1. So that's the main reason for increase the protection of the channel quality protection for these enhancement layers from top to bottom. And then we use a BPSK modulator to modulate the signal. AWGN channel is used as a channel, and then reverse operation is happening at the receiver side. So this is the summarized result. You can see that this orange one is for the equivalent JPEG system, where it failed after the noise variance of 1.6 completely failed. And even at lower noise variance, the proposed system is producing much higher gain compared to the equivalent JPEG one. So 18 dB PSNR against the 38 dB. So we have about 20 dB coding gain of the proposed one under different noise levels compared to the JPEG. So this is the main advantage of the proposed system is more robust against the channel errors compared to the JPEG. And the same performance can be observed for SSIM as well. Actually, SSIM performance is much better than the PSNR. So you can see the proposed system is much higher, has a much higher robustness compared to the JPEG for all different noise levels. And these are some of the visual representation of the images. Left side presents the proposed method and the right side for the JPEG. So you can see that the bit per pixel is also much lower than the equivalent JPEG one, but the quality is also quite poor on the right hand side. So which validates the proposed scheme for different noise levels. So this is for the base layer. The second set of images for the enhancement layer 1 and 2, 3, and 4 respectively. You can see bits per pixel is also lower for the proposed system. Quality is also very high, and the visual impact, visual representation is also increased quite significantly compared to the JPEG one. And these images were generated at the noise variance of 1.2. And that comes to the conclusion of the presentation. Here we have proposed autoencoder-based image quality measurement for the proposed system as well. And we considered PSNR and SSIM for measuring the performance of the system. And we have shown that the quality of the images generated at different noise levels is much higher for the proposed system compared to the equivalent JPEG representation. Thank you very much for your attention, and we are open, like I mentioned before at the beginning, we are open for collaborations in this domain. If anybody is interested in collaborating with us in any of the topics that I have mentioned before, and please contact me, and then we'll have joint research work either in publication now or for joint projects. Thank you very much, and here is my contact details for you to communicate with me in the future. Thank you very much again, and it was nice. It was pleasure for me to have a presentation in this conference, and hope to see you at some point in the future in another conference. Thank you very much.